Hey everyone and welcome. Today we're going to break down the LeetCode problem called longest harmonious subsequence. It sounds a little fancy, but don't worry, the core idea is pretty straightforward once we unpack it. We'll go from understanding the question to an efficient solution, step by step. Okay, so here's the problem statement. The key idea is this: we're looking for a harmonious group of numbers. What does that mean? It's just a fancy way of saying a collection of numbers where the difference between the biggest one and the smallest one is exactly 1. Our goal is to find the longest possible group like this that we can form by picking numbers from the input list. Let's look at this first example to really get it. The input is a mix of numbers, and the answer is 5. The explanation tells us the best group we can make is with 2s and 3s. If we gather all the 2s and all the 3s from the original list, we get 3 2s and 2 3s, for a total of 5 numbers. The largest is 3, the smallest is 2, and their difference is 1. That's a perfect harmonious subsequence. Our job is to find the pair of numbers, like 2 and 3, that gives us the biggest total count. So what's the first thing that might come to mind? Well, we could try to generate every single possible subsequence from the input list, and then for each one, check if it's harmonious. But that would be incredibly slow. The number of subsequences grows exponentially, which we often call big O of 2 to the power of n. For anything but a tiny list, this will take forever. We definitely need a smarter way. Here's the aha moment. A harmonious subsequence, by definition, has a max and min that are 1 apart. This means it can only be made of 2 unique kinds of numbers. For example, 2s and 3s, or 7s and 8s. It can't have, say, 2s, 3s, and 4s, because then, the max would be 4, and the min would be 2, and the difference would be 2, not 1. So the problem really simplifies to this. Find a number in the list, let's call it x for s, and find the total count of that number x, plus the total count of the number right after it, x plus 1. We just need to find the pair that gives us the highest sum. So how can we do that efficiently? A hash map, or a dictionary in Python, is the perfect tool. The plan is simple. First, we'll go through the entire input list once, and count up the occurrences of every number, storing them in our map. Then, we'll loop through the unique numbers in our map. For each number, we'll just ask, does the number that's 1 greater also exist in our map? If it does, we add their counts together. We just keep track of the highest sum we find, and that will be our answer. Alright, here's the full Python code for this approach. I know seeing a block of code can sometimes be a bit much, but don't worry. We're going to break it down into small, manageable pieces on the next couple of slides to see exactly how it works. Okay, let's start at the top. The first key step is this line here. We're using a helpful Python tool called a counter. All this does is go through our input list, which is called nums, and it automatically creates a frequency map for us. So if nums had 3 2s and 2 3s, our counts map would store that, 2 maps to a value of 3, and 3 maps to a value of 2. We also set up a variable to keep track of our best length so far, starting it at 0. Now for the main part. We loop through each unique number we found, which are the keys in our counts map. For each number, we do a simple check. Does the number that's 1 bigger than it also exist in our map? If the answer is yes, we've found a harmonious pair. We calculate its potential length by adding the count of our current number to the count of the next number. Then we just check if this new length is better than the best we've seen so far. If it is, we update our maximum length. After checking all the numbers, we just return whatever the best length was. So how does this approach stack up? It's really efficient. The time it takes is what we call big O of n, where n is the number of elements in the input list. This is because we basically just look at each element once to count it, and then we look at each unique number once. It's very fast. For memory, or space, it's also big O of n in the worst case, because we need to store the counts for every unique number in the list. So to wrap it all up, the key takeaway for this problem is to look past the complicated wording about subsequences and see the simple core requirement. We're just looking for pairs of numbers that are 1 apart, like 5 and 6, or 10 and 11. The best tool for this job is almost always a hash map to count frequencies. This lets us build an efficient solution, where we first count everything up, and then check for those adjacent pairs to find our answer. I hope that breakdown made the problem much clearer. If it helped you out, I'd really appreciate a like or a subscription. If you have any questions or another way to solve it, drop a comment below. And hey, if you're feeling extra generous, there's always the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next one.